This P1 video is about properties of waves and the wave equation. So first of all we need to know what a wave is. Well, a wave is just a disturbance which travels through a medium, that's the material it's travelling through, and the point is it transfers energy without transferring any matter. So if you look at the wave on screen, you can see that the medium is vibrating backwards and forwards and it's clearly transferring energy through it, but once the wave has passed, all the lines that are representing parts of the medium are back in their original positions, so there's no overall transfer of any material, just energy. So that's what a wave is, and there are two main types which you need to know about, which are transverse waves. And the characteristic of a transverse wave is it's the direction of vibration is at right angles to the direction of energy transfer. So as you saw there, the yellow dot was vibrating up and down, the energy transfer was to the right. Okay, we also need to be able to label key characteristics of waves. So the first of which is the amplitude, which is the maximum displacement of the medium. So if we're talking about a mechanical wave here, where there's actually physical displacement of the material, then you can see the blue line through the centre of the wave there represents the normal position of the material or the medium, and the white line is the position at one point in time as the wave is passing through. And you can see the little red double-ended arrow there is just the furthest away that it gets from its original position. So that's what we mean by maximum displacement of the medium. Another thing we need to be able to label is the wavelength, which is most commonly talked about as the distance between two adjacent peaks, right, or one peak and the next peak. But technically it's the distance between any two corresponding points on adjacent cycles that are next to each other. So we could do trough to trough as well, that's not a problem. And generally speaking, transverse waves can only travel in solids if we're talking about mechanical transverse waves through a solid material. Just another couple of labels on there, peak or crest and trough. And examples of transverse waves, the most important for the P1 module is the earthquake S waves. The secondary waves for an earthquake are transverse. And you can obviously produce one of these on a slinky, and I guess a Mexican wave would be an example as well. Light waves are also transverse, but of course the difference there is that there's not a physical medium that the light waves are travelling through. There's no substance that is vibrating. The light waves actually travel through something called the electromagnetic field. Okay, so the second type of wave is the longitudinal waves. This is the same as the original one we saw. And the key characteristic of this, as you see, is the yellow dot is vibrating left to right, and the direction of energy transfer is to the right. So the yellow dot is vibrating now in the same direction as the energy transfer is taking place. And that's the key characteristic of a longitudinal wave. Okay, so if we put the wave up a snapshot of it like we did with the transverse wave, then we can label similar things on there. We can label the wavelength. This time it's the distance between the sort of two places where it's compressed. We can't really label the amplitude easily on a longitudinal wave because you'd have to mark the original positions and the displaced positions of these lines, and that would get very messy. So again, instead of peaks we have compressions really, where the particles in the medium are closest together, and instead of troughs we have these things called rarefactions, where the particles in the medium are furthest apart. And examples of this type of wave would be P waves from the earthquake. So the primary earthquake waves have this characteristic where the direction of vibration is the same direction as of an energy transfer. And sound waves in air have this as well. And mechanical waves, again, you can make a slinky do this by pushing the end of it backwards and forwards rather than side to side like you would do for a transverse wave. So those are the two main types of waves, and the key thing about longitudinal waves, which is going to be really important when we talk about looking at the structure of the Earth, is that they can travel through any substance. Okay, so the one thing we couldn't really label on the diagram that was to do with waves is the idea of frequency. And what frequency is either the number of waves passing a particular point in a certain amount of time, or the number of vibrations in that time. Okay, so this is the equation to define frequency, and usually the time period we use is a second. And if we do that, then frequency is measured in units called hertz. So I'm just going to show you two different waves with two different frequencies. I'm going to use transverse because it's kind of easier to see what's going on. And you can count the waves that are going past as we do this, or you can watch the number of times the yellow dot goes up and back to its original position. So if we're on the first one, we've got one complete wave and a second complete wave. And roughly speaking, the time period that took was 6 seconds. So what we do is we say that's 2 complete vibrations of the yellow dot up and down, or 2 complete waves passing. They are the same thing. We take those number of vibrations, divide it by the time period that those vibrations took, which was 6 seconds, and we get 0.33, or 1/3 of a hertz. I'm going to show you another one underneath now to illustrate the point about the difference, and you can already see there's a difference with this wave. We're going to talk about that in the next slide. What happens is when you increase the frequency of a wave in a given medium, you also end up decreasing its wavelength. If you saw the slinky demonstration, you would have seen that. If you move the end of the slinky backwards and forwards quickly, you naturally get shorter wavelength waves. Okay, so this wave's going to go at the same speed to the right as the previous one, but because the waves are shorter wavelength, that will mean more waves passing in the same amount of time. So here we go. 1, 2, 3, 4, 5, 6 waves passing this time in the 6-second period. And unsurprisingly, that gives us a frequency of 6 vibrations divided by 6 seconds, which is 1 hertz. Okay, 1 vibration per second. The important thing to remember about this equation is this is not on the formula sheet. This is kind of considered a definition. You need to know what the definition of frequency is, and you can use it to work out frequency as a number. So very often, if they're giving you calculations to do, which we'll look at in a sec, they won't necessarily directly give you the frequency of the wave. You might need to work it out from the number of waves passing in a certain amount of time. Okay, so what we're going to look at now is this thing called the wave equation, which basically tells us what the relationship between wave speed, frequency, and wavelength is. And here it is. Now, there is a way to derive this from looking at the general definition of speed, but we're not going to do that here. Okay, so what we've got is the wave speed equals the frequency times the wavelength. Now, the important thing that you need to know for this part of P1 is what the consequences are of the fact that the wave speed doesn't change if you are travelling through the same medium. So if you've sent a wave through some steel, for example, provided it was the same type of steel, the wave speed would be constant in that steel. Same with water. Water waves, if the depth of the water actually remains constant and it's still water and not some other liquid, then the wave speed remains constant. So for a given medium, the wave speed is fixed. Now what that means is, if we change frequency, in order to keep this equation equal, we have to change the wavelength as well. And that's what we saw in the previous slide, where changing the frequency to increase the frequency meant we had a shorter wavelength. And you can see in the bottom left-hand corner the graph of this relationship, and it looks like a curve. And what this relationship is called is an inverse proportion. Okay, so I'm going to show you what happens as we change the frequency to the wavelength. So 2 things are going to happen here. In the equation, the words frequency and wavelength will get bigger and smaller to represent increasing frequency and decreasing wavelength. And the little cross will move up and down the line, so you can see how we can get this graph relationship between the two as well. So there you go, wavelength increasing, frequency decreasing, and then frequency increasing back again, and wavelength decreasing. And then they return to their original value. So what actually happens in this case, right, is that if you double the frequency, you will halve the wavelength. That makes sense from this equation, because let's say I had a wave speed of 10 meters per second and a frequency of 20 hertz, I'd have to have a wavelength of 0.5 meters. If I double the wavelength to 1 meter, to get the 10 meters per second back again, I would have to halve the frequency from 20 down to 10. Okay, so that's what happens with this relationship. In a given medium, for a fixed wave speed, which is what you get in that medium, the frequency is inversely proportional to the wavelength. If I double one, I will halve the other. Okay, that can be quite important. You are required to know that the frequency is inversely proportional to the wavelength and what that means. Okay, so they might, for example, give you a situation in which they tell you that it's the same medium and give you the frequency and wavelength of one particular wave and ask you to work out what happens to the wavelength if you do something to the frequency. And it will always be divide by the same number as you've multiplied. So 3 times the frequency will be 1/3 of the wavelength. 4 times the frequency, 1/4 of the wavelength. That's how those two are related. Okay, final thing then, some examples of using this equation in calculation. So what I've put up here is in the corner is the triangle for this equation. If you're not sure about how the triangle method works, you can look at the video. I'll put the video link up in this corner, which explains that with some examples. If you're completely happy with rearranging equations, you don't need to use the triangle, it's just here to help out. So we're going to look at 3 different questions for this. The first one, fairly straightforward, a water wave with a wavelength of 10 centimeters has a frequency of 4 Hertz. What is the wave speed? Now, whenever you're doing calculation questions, it's a really good idea to follow a procedure. And the best thing to do, because you remember you've got to have to pick which equation to use when you're doing this for real in the exam paper. You're not going to know which one to use in advance. So the first thing to do is to identify what you've been asked to find, in this case wave speed. And then when you look at the formula sheet in the front of the paper, you will have to use at some point an equation that has wave speed or speed in it. Now obviously we know which one we're using today for this one, but it's useful to do that so you can select. The next thing to do is to find the other information we need. Okay, we're just using it as normal form here. So remember the triangle, if you cover up the wave speed, it tells you that what you need to do to find the wave speed is do wavelength times frequency. Okay, so there are the other 2 pieces of information we need. We have a wavelength of 10 centimeters and a frequency of 4 Hertz. All you do then, write the equation down, underneath the quantities, put them in the right place. Now, you notice I've changed frequency and wavelength round from here. It doesn't matter which way round things are when you multiply them. Okay, they will give you the same answer no matter which order you multiply in. So we put the 4 Hertz from the frequency in the question in underneath the frequency, and we put the 10 centimeters under the wavelength. And when we multiply those together, we get 40. Now, here's where we've got to be careful. We've got to remember about unit consistency. We're working out a speed, which means that the unit will be a distance divided by a time. Frequency in Hertz is vibrations per second, so that means the speed will be something per second. The distance we've put in is in centimeters, so that means the length part of the speed will also be centimeters. Therefore, the units for this answer are 40 centimeters per second. Okay? Now, sometimes you'll get a free choice of units, but sometimes the space for the answer will have a unit filled in, so you've got to watch out for that. And if that happens, make sure you convert to the right unit. For example, if it had already said wave speed in meters per second for this answer, we would have to change the wavelength from 10 centimeters to 0.1 meters to make it standard units. So it's centimeters to meters, so you divide by 100 to get that. And that would make the answer 0.4 meters per second rather than 40 centimeters per second. Okay, and just generally speaking, if in doubt, convert to standard units first, as you can really tie yourself up in knots if you try and convert at the end sometimes, but particularly for some quantities. Okay, so that's number 1. Number 2, again, you can, if you want to, you can pause the video and have a go at these first, and then see if you've got them right. Now, this one again has some other little twists in it. First things first, again, find out the quantity we're trying to find. This time it's wavelength. So we cover up wavelength, and the triangle tells us that what we need to do is wave speed divided by frequency. So here are the other 2 numbers in the question. We've got 20 kilohertz and 340 meters per second. Now, the point I'm making with this question is that the words wave speed and frequency won't necessarily occur in the question. How do we know which one's which? Well, the only thing that we can do to tell that is look at the units. The units will have to be there. We need to know that frequency is measured in hertz and that speed is measured in meters per second, and then we can make the right substitution. Okay, so here we go. The wave speed is on the top according to the triangle, so that one goes on the top. Slight issue with the 20 kilohertz, of course. Again, if we're talking about our standard units, we've got to remember that kilo means 1,000, so 20 kilohertz is actually 20,000 hertz. When we do that, because we've got meters per second and hertz, which are our standard units, we will get our wavelength out in standard units as well, which is meters. So this is 0.017 meters, the wavelength of this wave. Okay, so the thing to notice from this one is make sure you know the units for all the quantities you need to use. If you don't know units, there will be some calculation questions that you can't be certain about where the numbers go. It might be simple in this case because you probably remember meters per second as a unit of speed, and the other number will have to go with frequency. But if you get lots of numbers with unfamiliar units, then you're going to have problems. So make sure you know for every quantity that you need for an equation, which unit does it go with. Okay. And the final question here is an example of sometimes how they can present information not written down as a number in a question, but graphically. Okay, so a couple of things here we can do. This is like breaking a code. So question 3, a wave travelling in the same medium as the wave in question 2 is shown below. What is its frequency? And I've put question 2 over here on the right, so you've got it for reference. So they could do this in the exam. This could be parts of a question, say. And what we've got to do here is decode it, because there's actually no numbers in this question at all for us to plug into our equation. So we need to work out where the numbers come from. If you end up in a situation like this, typical places, diagrams, graphs, or code words, if you like, that will give you the information you need. And I'll show you what I mean for this one. Okay, so again, we do know that we're trying to find frequency. So the first thing we do, cover up frequency in our triangle, write down the equation. What we've got to do now is find the wave speed and the wavelength. And here's how we do that. The code word in this question is same medium. If you remember what we said earlier in the video, if a wave's travelling through the same medium, it has the same speed. So that means, because we're talking about the wave travelling in the same medium as question 2, it will be moving at the same speed as the wave in question 2. So there's our speed, 340 meters per second. Second thing we need is wavelength, and for that we can get from the diagram. It says, it's shown below. We need to look at this diagram and see what the wavelength is. So there's a meter labelled on the diagram, and what we need to do is count the number of wavelengths. You remember it's corresponding points on the adjacent waves. So we start from a peak here, and we count 1, 2, 3, 4, 5 wavelengths. So that means, right, that 5 wavelengths is 1 meter, so a wavelength is 1/5 of a meter, 0.2 meters. And now we've got our numbers to stick into the equation. There we go, 340 meters per second again for wave speed, 0.2 meters for wavelength, and that gives us an answer of 1700 hertz when we put that in. Okay, so just be on the lookout for sort of cunning ways that they can ask you to find numbers to put in your equation, and you'll be fine. Thank you.